Here we have a system of particles, which could be a gas or a field of asteroids or anything for that matter, and it's moving about through space where we have a finite number of them. So there's n particles here, and they're each located by Ri for each of the ith particles. They each have a mass of mi, and from there we can define the center of mass as point G. And recall, to find a center of mass, we use the property of first moment, where a first moment is defined as the sum of the mi Ri for each particle, and we say that that would equal the total mass of the system times Rg, the centroidal distance, where the centroid equals the center of mass. And from here we can show that Ri, this vector down here, can be written in terms of the other two vectors as Rg plus little ri. And we'll use the lowercase r to indicate that it's measured from the centroidal axis. If we substitute that in for Ri, we get, and we can distribute this as the sum of the mi Rg plus the sum of the mi Ri is m total Rg, where here Rg is a constant and it can be lifted out of the summation. And the sum of the mi's will be m total. So this would become Rg m total. Now here, these are inside this series, so they stay there. Mi Ri is equal to m total Rg. If you look, we have the same term on both sides, so that can subtract away, and we get that the sum of the mi Ri is equal to 0. And that's important because it defines the centroid. The sum of all the first moments about the centroidal axis has to equal 0. And what it really says is that it's an equal distribution of the mass about that centroidal axis. For every first moment that a mass has on one side of the axis, there's an equal and opposite first moment on the other side, such that they all cancel out, and it's an equal distribution. So this shows how the first moment is used to define the location of a centroid or a center of mass, where the general process to find Rg is to do the sum of the mi Ri's over m total. And r here is a vector value, and if you do that vectorially, you'll get the vector solution for this. Keep in mind, for vectors, this could also be done as x values and then independently as y values, and the rgx and rgy that you find would locate this value up here. So you'd end up with this value as rgx, and this is rgy. So in 2 dimensions or even 3 dimensions, we can still use the same concept. If we look again at the first moment equation, we can take the derivative of both sides of this thing in time. And we're allowed to do that if it's a finite sum. And we'll assume that the overall mass of the system is constant, so that the derivative of the mass is 0, and we only have to worry about the derivatives of their locations. And we'll get that the sum of the mi Ri dots equals m total Rg dot. And recognize that r dot is v, so this becomes the sum of the mi vi's is m total vg. And if we look at it, we've seen mass times velocity before. It's momentum. And what this says is the sum of the individual momentum is equal to the total momentum of the system itself. So it's interesting that taking the derivative of the first moment, we come up with the momentum values for the system itself. Continuing on, we can take the derivative of the momentum equations, and we'll get the sum of the mi vi dot is equal to m total v of g dot. And recall that v dot is a, so this really says the sum of the miai's is equal to m total a of g, the acceleration of the center of mass. And over here, if we look at this, miai represents the force on each particle. So really what we're adding up on the left side here is all the individual forces that are pushing on each and every one of these particles as they interact up here. And that would look like F1 plus F on 2 plus F3 plus Fn, on and on and on and on. However, internally, if these are colliding, we have equal but opposites. So Newton's third law tells us that for every F1, 2 during a collision, there's an equal and opposite F on 2, 1, and they're going to cancel out. So all the internal forces will cancel, and only the externals will survive that summation. And what we find then is that this becomes the sum of the forces externally acting on this system equals m total a of g. And it turns out that this conclusion is really important. In introductory physics, we're taught that F is equal to ma. However, we're always doing that for small particles, little tiny wagons that they consider an individual particle all by itself. If we have a large distributed particle, let's say a big long beam or a piece of wood, and we apply a force to it, that force will only tell us the acceleration of the center of mass of that block. It won't tell us the acceleration at any given specific point on the block itself. So we do have to be careful when we're using Newton's second law of motion. It does only describe the acceleration of the center of mass of the system. If your system consists of one small car, that's not a problem. But if it consists of a large rigid body, then you do have to be careful about what this equation is telling you. And that is an important takeaway. It also tells us here that if there's a lot of internal forces and collisions going on with this gas that we've got here, we don't really care about the internal collisions, we just care about any external collisions. So if these gases are in some type of a bell housing, and they're exiting out of the bell housing, it's the collisions with the wall of the bell housing that are generating this acceleration, and the equal but opposite effect would propel the rocket forward. So we'd end up with a force on our rocket. So when dealing with a system of particles, we tend to track and follow the center of mass of the system and not really worry so much about all the individual collisions that are taking place. Let's take a look at a simplified example where here we have 6 masses of 1 kilogram each, and 2 of them have forces acting on them of 2 newtons and 1 newton. So let's see if we can track individual motions and also the center of mass values. For the lower mass, we'll call that particle 1. So the F on particle 1 is 1 newton. The acceleration of 1 would be force divided by m, which would be 1 newton over 1 kilogram. So we get 1 meter per second squared. The velocity for particle 1 would be the acceleration of 1 times the time, and we're told that these forces act for 10 seconds. So that would be 1 times 10, which would be 10 meters per second. And the distance traveled in the 10 seconds we can find from 1/2 at squared, which would be 1/2 times 1 times 10 squared, which is 50 meters. And we can do all the same for particle 2. So it's 2 newtons. The acceleration will be 2 meters per second squared. Its velocity will be 20 meters per second. And its distance will be 100 meters at that point. where our system would now look like this. Let's determine where the center of mass of the system is now. So x bar will be the sum of the mi xi's on m total. And we have then 4 of the masses haven't moved, they're back at 0. So 4 kilograms times 0 plus 1 kilogram at 50 meters plus 1 kilogram at 100 meters divided by the total mass of the system, which is 6 kilograms, which gives us an x bar of 25 meters. So we find that the center of mass right now is here. And from that, we can check that location by finding the acceleration of the system as F total on M total instead of doing the individuals. We have a total force of 1 Newton plus 2 Newtons over a total mass of 6 kilograms, which would be 3/6 or 1/2 a meter per second squared. And the distance that the center will have moved, 1/2 AGT squared, will be 1/2 times an acceleration of 1/2 times 10 seconds squared, 100 on 4. The center of the system should be located at 25 meters away, which it is. So we could track the center of the system instead of all the individual particles. And again, this was just a simple example to show how it works. If we had tens of thousands of particles, trying to track them individually would become too intensive, and it would be better to just track the center of mass of the system. So first moments lead us to a family of equations that work with systems of particles. The really important takeaway from all of this was that the sum of the forces externally applied to a system is MAG. That's worth remembering. We'll see that in the next section. Thanks for watching.